Most reverbs, algorithmic reverberators, call them what you will, from the 1980s onwards, owe a huge debt of gratitude to Manfred Schroeder, who in the 1960s set out to produce a mathematical model of what happens to sound in a real space. And simplistically, you've got, if you imagine a room with walls, you've got some echoes that come back off the wall, and then these are combined in some way to give a perception of space. And he broke this down into three main elements. One is an all-pass filter, and an all-pass filter doesn't colour the sound, but it alters the phase, so it kind of smears the sound out in time. A feedback comb filter is a very simple, very quick, very short delay, and then some kind of output mixing matrix that combines the various outputs of the comb filters in some way or other. And Manfred Schroeder suggested that the individual delays in the comb filters should be mutually prime. They're not prime numbers themselves, but mutually prime, so that they don't repeat and you don't get artificial peaks and troughs in the response. And then later on, people worked out that in fact it doesn't matter whether you put the comb filters first or the all-pass filters first. You do need the mixing matrix in some shape or form at the end, but these can be combined in any direction. Sometime around the year 2000, somebody who goes by the handle of Jezza developed a software version of the Schroeder reverberator, specifically using a number of what are really low-pass feedback comb filters feeding into a series of all-pass filters. So the comb filters generate your early reflections, and the comb filters filter them out. And he replicated this on both the left and the right channel, and developed something called Freeverb, which he set out to build because he says he wanted a good quality, studio quality reverb for him and his friends to use. He didn't intend it to be a commercial product, and so he gave away the code, and it's now public domain, which is very altruistic of him. And Freeverb has found its way into a number of commercial products over the years, and it's well worth reading his GitHub page where he explains his reasoning behind it, and also says interestingly that the reason that it sounds perhaps better than other algorithmic reverbs is that simply he spent a long time tuning the model until it sounded nice. And he also explains why he gave it away. He didn't want to be saddled with having to maintain it, and so he just made the whole lot open source. If we look at the all-pass filter first, this is the typical graphical representation of an all-pass filter. You've got a delay line of a certain number of milliseconds or samples, depending on your point of view. A certain amount of the input is fed forward to be mixed with the delayed output, and the delayed output, a certain amount is fed back into the input, and that's your feedback circuit. In software, this is pseudocode. This isn't real code, but imagine a delay of a certain number of samples. Then the all-pass filter, you're passing in an input sample and you're getting back out an output sample, and you're applying some kind of feedback. So we're reading from the output of the buffer here, and we're mixing that with a certain amount of the input to provide the output, and then we're saving back into the beginning a small amount of the delayed signal multiplied by the feedback. And then as we increment the read-write pointer from the buffer, when it reaches the end, it wraps to the beginning. So by setting the buffer length to a certain number of samples or a certain number of milliseconds, that's your delay, and then you just create lots of these and chain them together as your all-pass filters. The Freeverb comb filter is essentially a low-pass feedback comb filter, and you've got this feedback path, and it's slightly more complicated than the all-pass filter in as much as you're storing a previous result in what Jezza calls a filter store. So it's you've still got the delay line, so your input signal mixed with some signal from the feedback path, and remember there's the filter store in there, is delayed and then output. And in code, again, you're passing an input and returning an output and applying some kind of feedback, but you're also storing what I've called here in this pseudocode a previous result and applying damping factors to it. So this is in essence, the Freeverb implementation of the comb filter. In my implementation of the Freeverb algorithm, I've created these two structures, very similar to the Freeverb ones, but I'm having to read and write my samples from physical addresses in the PS RAM. I can't just create or malloc or calloc a buffer. I have to read and write from physical addresses. So what I'm setting is a base address for a particular buffer and its size and an index. So I'm using these to read and write. So I've got a structure for the comb filter, a structure for the all-pass filter, and then I'm combining these together into a composite structure that I'm calling PV for Parrot Verb Context. And the word context is, again, lifted from Freeverb. This is my implementation of the comb filter, for example, and as you can see, I'm using my PSRAM read and PSRAM write functions to read and write from physical addresses in the PSRAM memory. But essentially, this is exactly the same as that pseudocode I just showed. This is the function that processes an input sample, so we've got a left and right input, and it's just mixing those together and applying some kind of input gain to them. And then it's running through a number of comb filters, so there are 8 of these, and these are in parallel, so it's summing the output into a sum of the left output and the sum of the right output. And then the all-pass filters, it's running these through in series, so it's adding the output back into the input and round. And so I've got 8 of those and 4 of these. And then this is the mixing matrix where it's applying a little bit of the left channel to the right channel and the right channel to the left channel to give a sense of space. And the right channel is set a number of samples longer, so that also it's slightly spread in time. So the question is, what does it sound like? And I've got it on this algorithm switch on position E, so let's have a listen. And the answer is bloody awful. Oh, that's dreadful. I'm sort of getting more reverb as I twiddle knobs. Yeah, sort of getting some feedback. Sort of getting a bit of a wet-dry balance. But that's dreadful, so I'm going to have to find out what's going on here.